Hello, physicists. Today what we're going to be doing is we're going to be looking at circular motion. Now, right now in class we're working with uniform circular motion, which means circular motion going around a circle at a constant speed. The velocity is always changing because your direction is always changing. Well, we're going to be looking at circular motion that's speeding up. It's going to be kind of cool. Now, this is going to be weird to think of right now because you don't see the whole apparatus, but this is like a turntable. This is like a CD, like a record. It's going to go faster and faster and faster. Do you see the string? The string is going to be pulled, kind of like how you pull a lawnmower string. And it's being pulled because there's a mass that is falling down. And the mass falling down is pulling the string, is making this thing go faster and faster and faster. And then finally, this little knob here, which is a little rubber stopper that you use to put on force sensors, it's going to go flying off. Okay. So what I'm going to do is I'm going to do a video analysis of this. And I am going to plot the points of this right in the dead center until it flies off, and I'm going to quit. First thing I'm going to do is I am going to, well, first off, I insert the movie, okay, and then I click on the page auto arrange. And if I click on page auto arrange, boom, it goes like that. Now, what I want to do is I'm going to blow this guy up. So I'm going to make him as big as I can.
Something you said before, but I wanted to reiterate real quick.
Yes, sir.
Sometimes my students forget on the practical. When you want to open a file that has a movie in it, usually it's a CMBL file or a logger profile, you open the file. That's open right there. But in this case, we weren't doing that. We were inserting a movie file. It wasn't a logger profile, it was a movie we were putting into logger pro. So you go to insert and movie. So just to review, we talked about that before, but sometimes students forget.
Yeah, and the reason I did that was because it literally said by clicking insert arrow movie. And then I chose that movie. Good. Okay, one, set the origin at the center of the disk. Now, this little thing here gives you the buttons, or doesn't give you the buttons. Now, where do I set the origin? Again, if you put your cursor over and leave it a few seconds, it'll tell you what the thing is. So I'm going to set my origin dead center. Come on, I'm going to get my pixels perfect. I got the old man shakes. All right.
It looks pretty perfect to me.
Use the fact that the diameter disk is 9.45 centimeters. The actual circle, excluding my two nubs. All right, so what I'm going to do is I'm going to set my scale. And that's the set scale. So I'm going to go from one end across the circle to the other end. That is the diameter. It's going to ask me how long. Is it 1 meter? I'm going to say no. It is going to be 9.45 centimeters. It is going to be 0.0945 meters. Cool. Turn the page. Finally, I'm going to do the add point tool to mark the location of the stopper in each frame. Now what I'm going to do is I'm going to be plotting the center of the stopper. Okay, now at the start, the stopper is stationary for a while until the finger moves, and now it's starting to move. Okay, now this is really boring, so I'm going to shut up and do it. Hey, so what I've done is I have plotted all these points. You go, oh, okay, well, so I'm going to do my page auto again. Oh, look at that. What a mess. Yeah, and that's my X and M through time. All right. Well, yeah. With the data column, we're going to make some new calculated columns. Now, in order to do that, you go to data, and you go to new calculated column, okay? And when you do there, you can name something, usually it has a short name. Cool, you have units, meters per second, things like that. And what's here is for the expression, you are going to define what this is. Now, sometimes the grammar is a little bit different. There's no equals, you'll get used to it. You've got three different things you can use. One is a function. This way, if you want to say exponential, or a lot of these you're not going to use, but I'll show you the ones that you are going to use. Or what you can use is a variable. If you want to use like the x or the x velocity, we'll be using those a lot. Parameters, I've never used a parameter, so I wouldn't worry about it. So, we're going to figure out the speed of the stopper. All right, let me tell you what you know. You know the position in the x, you know the position of the y, you know the x velocity, and you know the y velocity. Boom, that's it. How do you know the speed of something? Well, guys, we've done vectors before. If you know the x velocity and the y velocity, is there any possible way you can tell me the speed of something? Think about the Pythagorean theorem. Isn't the speed like the hypotenuse of the x and the y velocity? Yeah. So if I were to give you a triangle and I gave you the x and the y, you tell me the hypotenuse. Yeah, wouldn't it be x squared plus y squared? Well, the square root of x squared plus y squared? So, I'm going to do the first one for you. If I'm going to call the speed for the name of it, I'm going to call it speed. Cool. Short name, they want to call it v, so I'll call it v. Units, meters per second. So I'm going to do m divided by s. The expression, well the function, I'm going to look for something that looks like a square root. SQRT. Cool. Now, it threw some brackets in there. So inside my brackets, I'm going to put in my variables. So my first variable is going to be x velocity. And it's going to be x velocity squared. So for me, my x velocity squared, I'm going to do the, above the 6. What do you call the above the 6, sir?
Caret?
Caret, all right. 2, so that's squared. X velocity squared plus, I'll just put a space in just so I can make it more readable, y velocity. Caret, above the 6. 2. And that should be it. I'm going to say done, and if I do anything grammatically wrong, you'll tell me. Boom. Now, if I take a look, I've made myself another column here. Speed, meters per second. And as I go in time, my speed increases tabulatively. What does this look like on my graph? Now, if I go to my graph here, and if I go to the vertical variables, if I left click, it will give me choices of one thing to do. So I'm going to choose speed. And that is what my speed versus time graph looks like. If I left click, I can choose 1. If I right click, then I get these graph options, all kinds of things like that. If I go to graph options and then axes options, what I can do is I can choose multiple things on there. For example, if I want to do x velocity and y velocity at the same time, then they'll show me that. That's a little funky. I'm going to go back to just my speed. Yeah. Okay, good. Distance r from the center of the disk to the center of the mass of the stopper. Huh. So if I pick a certain point here, and I want to know the distance, what I know is, I know it's x position, I know it's y position, I know it's x, I know it's y. And I want to know how far it is from the center. Guys, this looks like a triangle. Looks like Pythagorean theorem again. Wouldn't this r, this range, be x squared plus y squared? The square root of x squared plus y squared? Let's do it again. Data. New calculated column. I'm going to call it radius. And that is the distance the stopper is from the center. It's not the radius of the disk, it's the distance the stopper is. And I'm going to call that R. And what is its units? Meters. Legal.
And this works because the origin's right in the center, right? So it's the distance from the origin.
That was why it took me so long to make the origin the dead center, even with the old shaky hands. The expression, function, square root, variables, x, caret, 2, plus, variables, y, caret, 2, boom, done. And if you look, looks like 0.41 all the way. Hey, that's cool. You know what, I'm going to see what it says on the graph. Oh my God, look at that, that's awful. But is it awful? If you look at this, 0.0410 to 0.04105. So we're talking about tenths of millimeters. This is like, did I ever tell you guys about the time I put on reading glasses for the first time? I looked at my wife and I said, wow, you have pores. You know, that's not the thing you should ever say to your wife, or anyone for that matter. If you blow the data up, you're going to see stuff that you really shouldn't see. So what's the statistic? What's the average of all this? Well, what I'm going to do is I'm going to shade all this data here. And you don't mind me talking about life, do you, during lab, sir?
I don't mind.
Okay. And then let's analyze, we'll do a little statistics here. What's the average? Well, I got minimum of 0.40, and I got a maximum 0.42, and I got a mean of 0.414. You know what? For any formula that we need an average, we're going to use 0.04140 meters. Now, shouldn't it always be that? The answer is yes, it should always be that. Why isn't it? Well, a couple things. One is, probably don't have the best high-speed camera. When I was applying the points, didn't some things look a little funky? And second, I don't have the best high-speed hands either. So whenever we have an R, we're going to use 0.0414. Mark that down. Angular velocity. Well, V equals R omega. I want to know what omega is. Okay. Remember the relationship, V equals R omega. Omega is V divided by R. All right. Hey, new calculated column. Angular velocity. Cool. Short name, omega. Units, radians per second. Cool. Expression. I now have a new variable called speed. Now I could do speed divided by radius, but what I'm going to do is instead of speed divided by radius, it's going to be speed divided by 0.0414. Thank you. Dr. Johnson has so much better short-term memory than I do. So now, if you take a look at speed, cool. And if you look at angular velocity, the graphs look a whole lot alike. The only thing that's changed is the variables. Right? Centrifugal acceleration. Centrifugal acceleration is speed squared divided by R. How can you do that? Data. New calculated column. Centrifugal. Good. Short name, cent. Good. Units, meters per second, caret squared. Good. And this is v squared over time. So speed, caret squared divided by, excuse me, not v squared over time, v squared over radius. And for the radius, instead of using radius, 0.04140. Done. What does that look like? Whoa, that's funky. Now, this looks pretty good. But then you got a couple humps. What's going on in the humps? I think what you have there is you've got some camera angle error, or you could have some physical error too with your the person who's actually doing this, me, plotting points. All right. Note, the acceleration of the stopper is the vector sum of the tangential acceleration, which is parallel to the velocity, and the centripetal acceleration. Cool. So let's find out the tangential acceleration. The tangential acceleration is the change in the velocity with time. Well, let's take a look at the speed with time. Oops. Let's take a look at the speed with time. This part looks awfully linear. Well, I want to suggest two things to you. Either one, let's do a linear fit. That looks pretty gosh darn good. Or two, we could shade just part of it and take the linear fit from there. What do you say, Dr. Johnson?
I'd say the smaller one aligns with those points better.
Okay, I think so too. I think the smaller one aligns with those points better. So, what I'm going to do is I'm going to X. Am I Xing out the right one?
No.
No? X out this one.
Yes.
So,
It had a better root mean square. It had a better correlation.
I totally agree with you. I misunderstood you. So what we're going to do is we're going to say that this guy has an acceleration of 0.1466 at all times. It does not change with time. Way cool. I wish we had real people in real class to agree with that. Okay.
I agree.
Thank you, sir. Hey. All right. Now let's think about angular acceleration. Alpha. It's the change of omega with time. Well, let's look at omega. Oops. Let's look at omega. Angular velocity. Well, again, let's take a linear fit of that. That looks pretty good, doesn't it? Well, it should look pretty good because we're just taking that and we're just dividing that by r. Okay, so I think your angular acceleration is going to be 3.541 radians per second squared. Cool. That does not change with time. All right, let's look at centripetal acceleration. So again, for this particular answer, what you're doing is you're taking a linear fit. You can do the whole thing, you can do that little part where it really looks like a straight line before we get out with the camera errors. Good stuff. All right, centripetal acceleration. Whoa. Well, we found a linear fit with the whole thing isn't as good as a linear fit with that much. So let's do a linear fit now. I don't know.
That doesn't look very good to me.
No, it really doesn't. Because at the start, I mean, your x-intercept is like at 0.4. You got a big dip here. You got a... Oh, no, linear fit just doesn't work here. Mathematically, why wouldn't it work? Well, linear means that your exponent is 1, right? I mean, y equals x to the first power. And here what you have, this acceleration equals v squared over r. So, no, this slope changes with time. So you just can't do that. It does not have a certain slope. So next page, the table. How are we going to get the speed? Well, let's go to the speed graph. And let's do that linear slope again. Well, why do I want to do that? Because what I want to do is I want to go to about 0.5, and if I put my cursor at 0.5, close as I can, and if I put it right on the line, this is wicked cool. This will tell me what the speed is. Do you see, like in the lower left-hand corner, I got 0.502, that's the time, because that's the horizontal axis. What's on the vertical axis? 0.074, that's the speed. If I go to 1.5 seconds, I'm going to go like 1.5 here. And I'm going to go right on the line and do the best I can. Got the old man shaky hands. 1.503, close enough. What's that? 0.221? Guys, that's the speed. What is it at 2.25? Let's not use the data, let's use the line. 2.25? 0.367. Cool. 3.35? Use the line, don't use the data. 0.513. Whoa. All right, let's do the centrifugal acceleration. For the centrifugal acceleration, can we use the line? No, we can't really use the line. But what we can do is we can still use the cursor to find where 0.5 is.
Could we do a curve fit?
So we're going to do a curve fit. And what we said here first off is we are going to shade in this data here because we said that, come on, we said this data was the good looking data. And then it got kind of funky because we had the camera troubles. Now, we're going to curve fit and we say, well, what kind of curve? We had a v squared over r term. So since it was squared, instead of it being linear, we're going to do a squared fit. Okay? And so we try fit. And we say okay. And that's looking really good. In fact, I'm going to do this one more time. And I'm going to shave it just a little bit to here. And do that. Analyze, curve, quadratic. Try. Oh my, that's looking good. Correlation's 0.997. All right.
Looks good to me.
So now I'm going to take my cursor and I'm going to put it right on the line. 0.5, 0.18. 1.5 seconds, 1.10. 2.5 seconds. Again, I'm going to do the line. 3.18. 3.5 seconds. I'm going to do the line. 6.39. Now, one thing that's really cool about the tangential acceleration, the tangential acceleration is the same at all time. So take your value on the other page of A, and that's what it is down there. How do you find your magnitude of your acceleration? You add the guys vectorially. What do I mean vectorially? The square root of AC squared plus AT squared. So you find a half a second, the tangential is a major factor. At 3.5 seconds, it hardly makes a difference whatsoever. Okay, part 2, the forces, circular motion. Free body diagram, gravity down, normal force up. The only other force on there is your static friction. That's it. Your max static friction is your very last slide, just as flying off. That's it. Your max static friction at the very last slide equals m v squared over r. You know what r is? You know what v is? You know what m is? You can figure out your max stack friction. Hey, by the way, you know what Fn is. Well, if you know that, then I bet you can figure out what the coefficient of stack friction is. Isn't that cool? Okay, and that big circle thing, what you're going to do is you're going to kind of point, make vectors, and show the acceleration at various points. How do I know where they are at different times? Well, what I do is I take a look at my graph right here, and I see where I am at different times. For example, if I take a look at slide number 16, I'm at half a second. So I see where I am at slide 16. That's where I am at slide 13. At slide 16, I'm there at that position, about 8 o'clock. Where am I? At 1.5 seconds. At 1.5 seconds, I am at slide 46. Okay? Well, whoops. Then I'm going to keep moving this. And you see where it says up there 41 over 115? Okay, 47. There I am at slide 47. So at 1.5 seconds, about 1 o'clock. That's how I find my positions. And then finally, last two questions. In words, explain what happens to the magnitude and the direction of the stack friction force of the stopper from the time before it's moving, there isn't any, until the time it flies off the rotating disc when it becomes maximum.
This cut out. Plus 4.
We've got one last question. And define the coefficient stack friction. We already talked about that. So I'm good if you're good. We're done. It's lunchtime.